Hello everyone, I'm Tuan Vu from the Sorbonne University, and today I'm going to talk about annotations in the LLVM compilation flow. So to start off, some background motivation of this work. Program analysis and transformation tools often need additional information that they can't directly infer from the code. So annotations are used to provide the extra information to these tools. And the need for annotations may concern different application domains. For example, we got worst case execution time, so WCET tools need to know about the program flow information in order to perform their analysis. Or we can have crypto algorithms need to know about the which variables is secret, which one is masked, and so on. And there's another point worth noting is that annotations may be required at different representation level of a program, from the source to binary. And annotation languages have been proposed to, notably at the source level, specify program functional properties. However, there's been little effort to support non-functional properties about side channel or fault attacks, for example. Other than being used for specifying program behaviors, annotations are also used by compilers for different purposes. However, compilers generally do not emit annotations into the binary, except for WCET specific compilers. To better illustrate the diversity of program properties, I'm going to show you some interesting examples on an authentication code in the context of security against physical attacks. So we got the function verify PIN here. It compares the PIN code of the card against a code entered by a user using a comparison loop. And we insert a trivial loop protection here and to ensure the correct execution of the loop. And I know that it may seem silly to you, but it really makes sense when under fault injection. And then the function returns true or false, depending on whether the user has entered a correct code or not. So first, the very basic functional property, which is just the correct behavior of the function. And then we may have some non-functional properties, such as a secret PIN code, or a correct iteration number of the loop. And the loop protection doesn't only look silly to you, but also to the compiler, so it will get removed. And we just want to prevent the compiler from doing so. And here's what my PhD is about. We want to realize the full annotation workflow. And for this, we need a source level annotation language that covers a wide range of properties. And then we need an annotation aware that we decided to be LLVM based compiler, which know how to consume, produce, and propagate annotation. And finally, we need the representation of annotations at the binary level. So here's what we've done so far. Let's start with our annotation language. So our language is based on ACSL because it already allows specifying program functional properties. So for example, here we can annotate the function verify PIN using a logic predicate that expresses the correct behavior of the function. And then we introduce some semantic predicates to specify non-functional properties. For example, a secret card PIN parameter, or sensitive loop protection. And we also introduce some semantic variables to capture the side effects of the code. Here we got the count, which represents the iteration counter of the loop. In a nutshell, the annotation is defined by an annotated entity, a predicate, and potentially some predicate variables. Annotated entity can be either a function, a variable, or a C statement. A predicate is either a logic predicate, so a Boolean expression, or the semantic predicate that we just presented. And predicate variable is just a short name for variable referenced in predicate. So now we're going to see how do we represent it in the binary level. We all know that the debugging information defines representation of different entities of the source program into, in the binary level. So we're going to extend the DWARF debugging format to represent annotations. So a DWARF represents an executable program using a tree of debugging information entries or dice. And a die has a tag, some attribute, and potentially children. And we introduce new tags and attributes to represent annotations and semantic variables for it. And here's how an annotation die looks like. We have the predicate attribute. And for function and variable annotation, we have an annotated entity attribute. And as for statement annotation, we have the address range corresponding to the annotated statement in the source. And the children of annotation die are just predicate variables. So now, how do we transform the source code annotation into annotation dwarf dice using LLVM? And first, we define a representation of annotation, and then we define some mechanism to propagate them. LLVM already provides metadata mechanism, and debug info is also implemented using this mechanism. And it's even the only metadata that is preserved and emitted into the binary. So we're going to reuse it to represent function and variable annotations. As for search statements, although debug info does have a representation for it, it is too painful to maintain. So we're going to use annotation markers to delimit the region corresponding to an annotated statement. This mechanism is inspired by lifetime markers, already existed in LLVM. So the semantics are all instructions from a start marker to a corresponding end marker are annotated. So we define new type of metadata for annotation, and here's how a function or variable from annotation metadata looks like. It contains a predicate, a reference to the debug info metadata for annotated entity and for the predicate variables. And the annotation metadata is created, propagated, and emitted to the binary using the same mechanism as debug info metadata. As for statement metadata, statement annotation metadata, the only difference is that it doesn't have annotated entity, but instead it is embedded in the annotation markers. So now we're gonna deal with the real problem, is that how do we preserve and propagate annotations in the middle end and the back end of LLVM? So what does it even mean, preserving annotations? So we define it here. Preserving the annotations means preserving the annotated entity, the predicate variables, and the annotation metadata itself. Preserving annotated entity means maintaining the correct debug info for annotated variable and function, or maintaining the correct annotated region for statement annotations. Preserving predicate variables is maintaining the correct debug info for all these variables. As for the annotation metadata, it is kept aside from the code and doesn't interact with optimizations, so there's no reason that it should be removed. So we can see that we have two different types of problems here. The first one is related to debug info propagation. Because we all know that maintaining debug info is best effort and there's no real guarantee for it. Plus, we can have implementation bugs. So, however, our biggest hurdle is to have a correct location ranges for auto variables. And even if we can make it, we can still perform an analysis on the generated binary to recover this information. So for now, we're going to assume that the debug info is correct. And the second type of problem is the statement annotation propagation, because annotated instructions may be removed or merged with not annotated instructions, or even with instructions annotated with a different annotation. So how do we preserve an annotated region? We first have to figure out what preserving an annotated region even mean. So we define an annotated, we say that an annotated region is correctly preserved when two conditions hold: the isolation conditions and the optimization conditions. The isolation conditions basically mean just no instructions should be moved across the annotation markers. However, the annotation markers only guarantee this condition for load and store instructions and instructions with side effects. What about the others? So we came up with the concept of SSA barriers. Let's consider a top region that defines the SSA variables A and B. We have the annotated region, which is delimited by the markers here. And the annotated regions uses A, B, and the constant 3. To prevent B from getting into the annotated region, we insert an annotation use of B right before the annotation marker. And to prevent C, D, and E from moving into the top region, we insert a definition of values used by C, D, and E right after the annotation marker. So, and we do the same thing for the end markers. So now we got a correctly isolated annotated region. So here's our current implementation. Clang emits annotation metadata and markers. SSA barriers are emitted currently by mem2reg. And in the IR level, the markers and the barriers are represented by intrinsics with side effects. In the MIR level, they are lower into pseudo instructions with side effects. The markers are used to compute the address range for annotated statement at the moment of debug emission. And while the barriers are constrained to have the same source and destination register, so they can be safely removed at the moment of machine code emission. So we just seen how to guarantee the isolation conditions. Now let's take a look at optimization conditions. By default, the annotated region is optimized at the same level as other regions, but this can be changed. For example, we want to have no optimization at all in the annotated region, or we can have less optimization than the default level. For the no opt behavior, this can be guaranteed by inserting SSA barriers inside the annotated region. And however, the ideal solution is to have a per region optimization mechanism. So we tested our implementation following these 3 steps. We first annotate the source code, and then we compile it at O2. And finally, we verify manually in the binary the following information. We look for the annotation die, for the correct debug info for annotated function or variable, and for predicate variables. And for statement annotation, we also verify the machine code generated for the annotated statement. And we have tested it for these applications. We have 3 different versions of verify pin. The first one, without protection, we just annotate the function behavior. Then we have 2 different protections, a control flow integrity and the trivial loop protection that I just showed you. And for these, we annotate the protection, so to make sure that it doesn't get removed by the compiler. For the first order masked AES, we annotate the secret and the masked variables. For RSA and SHA, we annotate random functions and variables, so it's some sort of fuzzing. And the results are quite positive. We have found the annotations in the DWARF section. At first, some auto variable location range was incorrect, but I submitted a patch to fix the bug. And we also find our protections in the machine code, and we are pretty happy about it. Speaking of preserving protection, we all know that protection can be removed by optimizations. So traditionally, we have 2 solutions to this problem. We can either compiling without optimization, or we can use fragile programming tricks. So we did some preliminary comparison with the code generated, and we simulated it for ARM Cortex M3. And here's the result. code compiled at O2 with annotation does preserve the protections, and it's faster than the code generated by two traditional solutions. Code compiled at O2 alone without anything is fastest because it doesn't have to execute the protection. It's already gone. And to conclude, we have defined an ACSL-based search-level annotation language that covers a wide range of properties. And then we introduce some mechanism to get closer to an annotation-aware compilation framework. And finally, we extend the DWARF format to represent annotation at the binary level. In the future, we'd want to evaluate the impact of annotation propagation on the compiler performance and on the generated code performance. We also want to automate the process of validation of annotation, and we want to explore some mechanism to have a per-region optimization control and graduation as well. So here's some references used during this presentation, and thank you for your attention.
Any questions?
Great presentation, thank you. So just a quick question. So can you annotate loops with loop invariants with what you currently implemented?
Okay, so if I understand correctly your question, I'm going to show you what have been implemented so far, right?
Right. So you know, pre and post conditions I see you can do, but can you do loop invariants? And maybe you can, maybe I missed it, but I'm curious what the answer is.
I'm sorry, can you read?
Can you annotate loops with loop invariants?
Loops, invariant?
Yes, loops
okay.
with loop invariants, yes.
Yes, we can.
Okay.
We can absolutely do it.
Thank you.
Thank you for your talk. So I'm just interested. So I'm not pretty sure, but you talk about the ideal solution for the region is to have like per region optimizations.
Yeah.
What about like extract the region into like separate functions? Like I'm not talking about like change the program, but like you can create a temporarily extracted functions.
I see. Yeah, that's one solution.
Yeah, and I think it can also solve the SSA barrier you propose, like because when you extract the functions, the current utilities will handle all those inputs data and outputs data.
I see.
Yeah.
I see. Yeah. So it's maybe that's a possible solution, alternative to the SSA barriers and stuff. We'll get to dig deeper into the implementation of it, but yeah, definitely.
Okay, great.
Good
Thanks.
solution. Thank you.
Quick question, maybe I missed it, but what is the point of preserving the annotations at the binary level, like in the DWARF information? Is there tools that then use that information, and for what? Can you?
Binary analysis tools often need to know about which properties to verify in the program, in the binary, in the executable binary. And as I said earlier, the worst case execution time domain really needs to know about the flow information. So for example, the loop bound and the statement execution frequency in order to compute the worst case execution time.
Okay, thank you.
Thank you.
Let's thank the speaker.
Thank you.